So just one chapter for this exam. And we're looking at atomic structure and periodicity, right? How the periodic table's constructed. It's constructed based upon the building of atoms. Now, when Mendeleev started, he didn't see that in its future, right? But now that we know more, then we're able to actually, the table is more powerful than it was when he put it together. All right. So let's get moving. Which form of electromagnetic radiation has the longest wavelengths? Either you memorize it or you rationalize it. If you have a spectrum, right, and this is the wavelength gets bigger that direction, then the longest wavelengths are going to be radio waves. And the shortest ones are going to be gamma rays. Sometimes we do like that. That's a gamma. And that's a bad gamma. You do a better gamma. Here we go. And so, are either one of those up there? The longest radio waves, radio waves. Those are the longest ones, right? And in between, we have visible range here, right? And this direction, we have infrared, and we have microwaves. And on this end, we have ultraviolet, and then X-rays and gamma rays. You heard the gamma ray burst? You heard that in the news?
Heard of it.
Yeah, it's a phenomenon that's produced by extremely energetic phenomena in way outer space. There's some speculation as to what causes it. Maybe two black holes crashing into each other, or a star collapsing, something. But it's very directional, and that's why we haven't had to worry about the gamma ray bursts here, because it's a big place, and you've got to be right in the bullseye to feel the effect. But if one ever comes our way, then we're in huge trouble, because light years away, it's still got enough power to cook our atmosphere. That's the gamma ray. Oh, by the way, which way does the energy increase for these photons? That way, right? Yeah, energy increases this way. And that's based upon Planck's equation, right? Energy equals Planck's constant times frequency. So if the frequency goes up, the energy goes up, and frequency is very, very high here. Okay, enough said about that. Well, that's a stubborn marker. 3. Which of the following frequencies, maybe I can read it better that way, corresponds to light with the longest wavelength? Oh, okay. So if we have, remember the relationship, speed of light equals frequency times wavelength. So they're inversely proportional. So the frequency corresponding with the longest wavelength, as this gets longer, this gets shorter, this gets smaller, that gets bigger, this gets smaller. So the smallest frequency will be the longest wavelength. So I look at the powers of 10 first. Right. So got any that are the same? No, they're all different. So we can rationalize this one just from the powers of 10. So the smallest value here would be the biggest value there. Smallest frequency here would be 10 to the 5th, B. And if you run across 2 or more that have the same powers of 10, then you go to the coefficient and break the tie. All right.
So the coefficient, would the highest coefficient be the right one or the lowest coefficient?
Lowest. In this case, lowest, yeah. Because you want the smallest number.
That's the next question.
Yeah. Here we go, number 6. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. So the wavelength is given as 254 nanometers. All right. When mercury emits a photon of light at this wavelength, the frequency of this light is. So we're looking for that one. And since C equals that times that, we can solve for this one. Equals C divided by lambda. The trick to this one is recognizing that's not an SI unit. That's a derived unit. So we need meters here. Okay. So when you have something like that, the easiest way is say, what's a nano? A nano is 10 to the minus 9 or a billion. So I can say 200 and let's see. Speed of light is what? 2.9979 times 10 to the 8 meters per second. And then this one would be 254 times 10 to the minus 9 meters. You don't have to convert it to scientific notation to plug it into your calculator. Right. And once you do that, I have to get my calculator out first. 2.9979 exponent 8, all right, then divided by 254 exponent minus 9. I get 3 significant figures. Or perfect. It doesn't say what the units are, does it? 1.18 C. Oh yeah, there they are. Tacked on to the end. Reciprocal seconds, same thing as hertz. And these formulas, I believe, are in useful information. Well, that means they'll be available on the test. Let me just check to be sure. Here we go. So, yeah, there it is. Okay. All right, so let's go to number 8. Green light can have a wavelength of 543 nanometers. Wavelength of 543 nanometers. Why does it say green light can have a wavelength? Because green is our physiological response to the light. And we can think it's green when the wavelength shifts a little bit. Now, I don't know about, this is going to sound sexist, but green to me is green, right? To the ladies, this green is different from that green, it's different from that green. And I don't stop at a green light. I mean, I don't go from a green light at the traffic signal. I go at a blue light because I'm colorblind. Okay, let's get back to the question.
My uncle's colorblind like that too.
I'm sorry?
My uncle's colorblind like that too.
Yeah, I mean, it's not real bad. I can see a little bit of green in it, but it's not as intended, I think.
Yeah.
The energy of a photon of this light is, okay. So we want the energy, right? This is one expression. What's the other expression? Planck's constant times C divided by lambda, right? Derived from the relationship of frequency and wavelengths and the speed of light. Okay, so now we still have to convert this, though. Right. 543 times 10 to the minus 9 meters. Okay, we just need Planck's constant. So what's Planck's constant? It doesn't say there, so you have to look it up. It's in the back. Useful information. Planck's constant. Oh, where did I put it? Conversion factors, densities, formulas. I know it's in here. There it is. 6.626 minus 34. 6.626 times 10 minus 34 joules seconds. And then we have speed of light, which is the same as it was a few minutes ago. Meters per second. And wavelength. 543 times 10 to the minus 9 meters. Okay, let's check our units. We're going to want energy units, right? So we want this one to stay and the rest of them to go. So this is in the denominator, that's in the numerator. That's good. Numerator, denominator. There we go. So the units are right. They check out. Okay. Okay. So now all I have to do is crunch numbers. 6.626 exponent minus 34. 2.9979 exponent 8 times, and then divide by that. 543 exponent minus 9. So I get 3 significant figures. 6 times 10 to the minus 19 joules. C. Okay. And I could just say, this is how you set it up, and there's the answer. But I've learned, unless I'm pressed for time, I've learned that I need to do these each time because sometimes I put the wrong answers up there. I make a typo or something like that. Some innocent mistake. Not malicious. And this is a good way to check myself and keep the document accurate. All right, 8. Let's see, how about 11? I need to scroll a little bit there. Yep. How many of the following is or are correct? Of 11. All right, so we got I, and B. That reminds me of some movie, Gremlins. Guy that drove the tractor. Y'all haven't seen Gremlins? Oh, you got to go see Gremlins. Get it? I mean, it's old enough. May even be free on the internet. Never mind, it won't make any sense to you until you've seen the movie. Okay, back to the topic. The importance of the equation E equals mc squared is that energy has mass. Yeah, I go for that. Yeah. mc squared, that's what Einstein was saying. They're interchangeable. Matter, mass, and energy are manifestations of the same thing. How about electromagnetic radiation can be thought of as a stream of particles called photons? Yes. All right, that's the particle nature of light. Electromagnetic radiation exhibits wave properties. Yeah, it does that too. Energy can only occur in discrete units called quanta. Indeed, it can. That is what gives us the clues to the structure, the electronic structure of atoms, because light only comes off in packets. certain discrete amounts, and that's based upon the movement of electrons in orbitals around the atom. They can't go in between. Right? What would happen if the electron could occupy any position around the nucleus? It could be here, 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 any place. And the only kind of light we'd ever get is white light, because you get a mixture. I mean, you could go out here and then jump back here, 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 here. It'd be a mess, right? Then we wouldn't be able to determine anything about the universe. But instead, there are discrete levels, and this quantized energy, which was proposed by Niels Bohr, is due to the movement of electrons. So they're all true. Actually, I did a little reading over the last week about the, it had something to do with this, but it's more expansive. It had to do with quantum mechanics. And I think we're going to get into that, aren't we? That's the last two chapters. Yeah, bonding. Yeah, we're going to talk about that. But one thing that I discovered was the development of these concepts took decades to hammer out the details and to fix the quirky things. And it took dozens and dozens of big brains to do it. Anyway, let's move on. 12. Let's see, we're going to need that. From the following list of observations, choose the one that most clearly supports the conclusion for the following 4 questions. Okay. Electrons have wave properties. And we're going to look at that list of A, B, C, D, E and say, which ones of these support the wave property of electrons? And notice we only have one choice, A, B, C, D, or E. I mean, there's no 2 of the above, none of the above, that kind of thing. So once we find our answer, we're done. Electrons have wave properties. Emission spectra of hydrogen. I don't think so. The emission spectrum of hydrogen has 4 lines, 4 visible lines. And those lines represent those discrete movements. Right? Has nothing to do with waves. It has to do with particle movement. How about B, photoelectric effect? Well, that's another particle nature of light. We're looking for wave nature. Scattering of alpha particles by metal foil. What are they referring to there? Pardon my English. That's pretty bad. Rutherford's gold foil experiment. He fired alpha particles at metal foil, and most of them went through, but some of them bounced off in all kinds of directions, which supported his nuclear model for the atom. Right? That's not wave property. Diffraction. Ha! There you go. Diffraction. What's diffraction? Diffraction, actually, this is a good way to do it. You got a beam here, a solid thing, and you got a detector out here. Okay. So the light wave's coming along. We've managed to make it flat. We've collimated the beam. When it reaches this one, this edge serves as a point source for a wave. So the waves now start propagating from that, like that. And instead of having a discrete line here, where it's light here and dark here, okay, we get gradations. It's lightest right here, and it gets darker as you move away. Okay, that's diffraction. either past an interruption like that, or through a slit, or through a pinhole, you get the same effect. So that's the answer, D. How about, let's see, yeah, 13 also. So what do we, not 113, 13. There we go. So let me scroll up just a little bit. Oops. Oh, we got 14 also. Electromagnetic radiation have wave characteristics. Actually, the only one that fits that is diffraction. The rest of those have to do with particle nature. Cathode rays, we didn't get to that one, but cathode rays are electrons. And what do cathode rays do? Well, besides, you guys are too young to remember picture tubes, sorry, televisions with picture tubes, or do you have an old one sitting around somewhere? No, it's all flat screens for you guys, right? I remember picture tubes, and if you got one that big, you were doing good. Right? Cost a lot of money, and they had the whole tube. This was the picture was. Huh?
I got 2 amp.
Well, they had amplifiers, yes.
The two little ones, that's the tubes.
No. No, the picture tube was big, and it projected images on the front surface. Right? And it did that by at the back of the tube, they were slightly curved, and at the back of the tube here was an electron gun. And it fired electrons, it accelerated them through an electric field, and then it used magnetic, maybe even electrical, control in 2 dimensions, so that we could fire an electron up here, right? And the phosphor on the back of that screen would light up, okay? And the electronic would control and scan across that screen. They still do that scanning only on flat screens. It's basically the same thing. But when that electron hit the phosphor, it would light up. And it did so because it had energy, right? It struck the phosphor, it gave up its energy, and the phosphor lit up. And they were so finely controlled that you could have 3 phosphors together. 1, 2, 3. Let's see, what are the primary colors? What are red, yellow, and blue? Okay, red, yellow, and blue. So they could control it to where the electron would strike one of these or one of these, or they could strike this one and this one in rapid succession and give you, your whole range of colors. But these picture tubes were based purely upon that electron gun being controlled and firing electrons, which have mass and energy, as a matter of fact, kinetic energy, right? They're not behaving as waves here, they're behaving as particles. Computer screens used to be that way, and they were heavy. They had to be made out of thick glass because inside that tube was a vacuum. You couldn't fire electrons through atmosphere. I mean, they move a fraction of a centimeter and get absorbed by some air molecule. So it had to be a vacuum. That means you had to have thick glass to keep it from imploding. And if you had one that was end of its life, and you set it out in the field and got off far enough and shot it with your rifle, you hit it with that bullet and it would explode. First, actually, what if you had a camera that could film fast enough, you'd see it go and then out, because it would pressure on the outside would crush it, and then it would rebound. Okay, so 13 is also D, wave properties, diffraction. Electromagnetic radiation has wave properties. Okay, it does. And we know that because of diffraction. Electrons in atoms have quantized energies because of what? The primary clue for quantized energies of electrons in atoms is the line spectrum of hydrogen. So we got 12, 13, and 14. Oops. 14, 15. Oh, we got another one. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. The key there is wavelength. If you're talking about waves, you're talking about diffraction in the choices that we have. Are we going to get off this mountain? Yeah, here's 16. There we go. So this was 13 through 15, wasn't it? But I did right up there. 16. Okay. The four lines observed in the visible emission spectrum of hydrogen tell us that. Well, that's another way of saying what we've already done. It's another way of telling us that only certain energies are allowed for electrons in the hydrogen atom. But we've since learned that that's true for all atoms. Electrons move from one level to the next, and there's nothing in between. So that was D. 17. Okay. For which of the following transitions does the light emitted have the longest wavelength? So we want the longest. Spell longest wavelength. The way to think about this one is the longest wavelength means the smallest energy. Right? Smallest energy means the shortest jump. The electron makes the shortest jump between levels, would give us the longest wavelength or the lowest energy. So let's look what we have choices here. The shortest jump. Remember, the first level is, if it's right here, then the second level is way out here. And the third level is even closer. And the fourth level is even closer than that. Okay. So really the shortest jump is between levels out here. If you got anything going to the first or the second level, then it's going to be the wavelength's too short. Okay. So 4 to 3, 4 to 2, 4 to 1, 3 to 2. No, 4 to 3 would be the shortest jump. Yep. So that would be the smallest energy, longest wavelength. Okay, 18. When a hydrogen electron makes a transition from n equals 3 to n equals 1, which of the following statements is true? So we're going from n equals 3 to n equals 1. Which of the following is true? Okay, so more than one might be true. You should look at the selections. You could have two of them true at the same time. Energy is emitted. Is that true? From a higher energy to a lower energy? Yeah, energy would have to be emitted. We still have to conserve energy, even though we're at the subatomic level. All right, so 3, high to low, means energy emitted. That's true. So that's Roman numeral 1. Okay, that one's good. Energy is absorbed, can't have both of them. So one or the other. The electron loses energy. Yeah, if it's going to emit energy, it loses energy as it gets closer to the nucleus. All right, so electron loses energy. That's 3. 3. Yeah, that was true. Okay. No, I can't have both. Electron cannot make this transition. Okay, I think we were searching for something to fill in the blank. So it's 1 and 3. 1 and 3 is B. Okay, 21. Which of the following is incorrect? The emission spectrum of hydrogen contains a continuum of colors. No, no, it's a line spectrum, not a continuous spectrum. The light from the sun is a continuous spectrum because it's got transitions of many different elements combined into one. The emission spectrum of hydrogen is a line spectrum, not a continuum. So A is false. Now let's see. How about the others? We don't have any oddballs in there, like 2 of the above, none of the above, that type. Okay, so we can stop. We found our answer. How about 22? Here we go. Which of the following statements best describes the Heisenberg uncertainty principle? You remember that one? Let me see if I can remember the formula. Let's see. Positional error and momentum error, which is actually, we wrote it this way. Mass times velocity. That's momentum. Is it less than or equal to or greater than or equal to? I don't know if I put that in useful information or not. I don't see it. I think it's less than equal to. R over 4 pi, or 4 pi over R, I can't remember which. The Heisenberg uncertainty principle says what? Well, let's just run down. The exact position of an electron is always uncertain. Is that true? Not according to the principle. Right? You can know the position of the electron, but if you do, you don't know how fast it's moving. You don't know its energy. Okay. The velocity of a particle can only be estimated. No, you can know it. You can know it with great precision, but then you don't know where it is. That's kind of weird, isn't it? I don't like having that up there because I'm not sure what it is. It's impossible to accurately know both the exact location and the momentum of a particle. That's the one. You can't know both at the same time because of the size of the particle. If the particle is very small, let's go the other direction. If the particle is very big, like me, then you can know my momentum and you can know my position with fair accuracy because of its this, I can't say equivalence, but this relationship with that constant value. All right, so we found our answer. C, that's the Heisenberg uncertainty principle. It only becomes a difficulty when you're down at the very small level. All right, scroll just a hair and we can get, how many can we get up here? Oh, we can get 3. Let's do it like that. There we go. 25. How many f orbitals have the value n equals 3? All right, n equals 3. So what's an f? Well, we've got what? We've got n, we got l, we got m sub l, and we got m sub s. Those are 4 quantum numbers, remember? Okay, how do we find this one? We take that one and start from 0. Go 1, 2. Okay, and this is an S, this is a P, and this is a D. Right, so there are no F's. For n equals 3, there are no F's. You have to have at least 4 to get out to the 3, which is F. So the answer here is 0. There are no F orbitals at n equals 3. That was a trick question. Okay, I suspect I'm going to need those again, so I'm going to leave them up there. 26. How many f orbitals have n equals 6? Okay, now we got 6. And we can have 0, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay. So which one of these is F? S, P, D, F. Here we go. So there you got your F orbital. How many F orbitals have n equals 6? So how many of these can you have? Well, we go to the m sub l level, right? -3, -2, -1, 0, +1, +2, +3. 1, 2, 3, 4, 5, 6, 7. 7 orbitals. Okay, B is the answer. Now, actually, it doesn't matter n equals 6. It just matters, do we have an f orbital there? And if n equals 6, yeah, we have an f orbital. But you can have f orbitals with lower n's. And then, how many orbitals can the f have? Well, once you got to f, then it's this many. It's always 7. That's why you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 down here. These are all f orbitals with plus half minus a half. 2 electrons for each one gives you 14. Okay, 27. Let's see, if n equals 2, how many orbitals are possible? Well, if n equals 2, we can have 1, 0, and 1, right? These are orbitals. M sub L's, those are orbitals. So we can have how many here? Just 1, right? So we can have 1 here. And this one, we can have -1, 0, +1. So we can have 3 there. So we can have 4 total. That's B. Okay. Well, I put a 1 there for that's just how many you can have. Actually, the value is 0. M sub L has to be 0. Right? -0, 0, +0. Let's see. I'm going to need some more of these before I erase. I better check. Yeah, 28, 28, and 29. A given set of p orbitals consists of a number of orbitals, given set of p's. Okay, so if we're at p's, that's s p, that's 1, l equals 1, right? Okay, so that means -1, 0, and +1. So you have 3. C is the answer. And then 29. Which of the following is an incorrect designation for an atomic orbital? Okay, so we have to do We have to do A through E. A, B, C, D, E. First one, 1s. We're looking for the incorrect. Is that correct? Yeah, you can have an s orbital for 1. That's good. How about B? 3d. Well, 3 is going to be this one. So 3 would be 0, 1, and 2. And SPD. There you go. Yeah, that's correct. How about 1p? Can you have a p orbital of 1? No. Now, if you have 1 here, you can only have 0 and 1. That's SP. Excuse me. If you have 1 here, you can have a 0. That's it. That's it. 0. You go up to n minus 1. Right. So this one's wrong. Oh, we found our answer. 4 F's, yeah. You have a 4 there, you can have a 0, 1, 2, 3, S, P, D, F. So that was good. And 6S, yeah, you can have S's in any n level because we're building from the bottom up. So 6 can have S, 5, 4, 3, 2, 1, all of them can have S's. Only 2s can have P. 2 and up can have P. 3 and up can have D's. 4 and up can have F's. Nothing below. All right. All right. So we scroll to the next one. 31, 32. I do a little time. Running short, of course. 31. A point in the wave function where the amplitude is 0 defines what? Remember when we were drawing the representations for, say, the s orbital. And for the 1s, you have no 0 probabilities in it. For the 2s, you have one place where there's no probability of finding electrons. It's called a node. So it goes like this and like that. And then if you have a 3s, I think it goes something like this, like that, something like that. So take the number for the s orbitals anyway. Take the number, the n number, and subtract 1. And that's how many nodes you can have. So 1 has 0, 2 has 1 node, 3 has 2 nodes, 4 would have 3 nodes. So the answer here is the node. And the amplitude is like this curve where you can have 0 probability of finding electrons. That doesn't mean they're not there. It just means the probability that you calculate is 0. Okay, 32. How many electrons in an atom can have the quantum numbers N3, L2? So N equals 3 and L equals 2. How many electrons? Maximum number of electrons have quantum numbers 3, L2. Okay. So remember Pauli exclusion principle? No 2 electrons can have the same set of 4 quantum numbers. Now they can have the same this one and this one, but from then on, we've got to differ somehow. So M sub L would be what? Well, for 2, you can have -2, -1, 0, +1, and +2. And then for each one of those, you can have +1/2 and -1/2. So we have 2, 4, 6, 8, 10. You can have 10 electrons. And they'll each have their unique set of 4 quantum numbers. Let's see. think the next one is yellowed. 33. How many electrons can be described by the quantum number N3, L3, M sub L to 1? Oh, wait a minute. N3, I better work this one out. N3, L3. That can't be. Right? L can only be 0, 1, and 2. So the answer to that 0 is a trick question. No electrons can have that. 34. What is the L quantum number for a 4s orbital? Oh, okay. The L, the quantum numbers are given letters, right? So what's the number of L that is S? 0. Okay. All S's are zeros. Okay. Let me see here. 37. Which of the following combinations of quantum numbers N, L, M sub L, M sub S do not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom? Which combination of quantum numbers is not allowed? Okay. So we just need to find the one that's not allowed. 9, 8 minus 4 half. 9, 8 minus 4 plus 1 half. Okay. 9. Right, N's 9. So L could be 8, 7, 0, 1, 2, 3, 4, 5, 6, 7, 8. That's true. And then if we have 8, can we have minus 4? Yeah. Yeah. So this one's okay. How about B? 8, 2, 2, 1 half. 8, 2, 2, 1 half. Okay. 8. Yeah. 2's, it catches the 2. And then 2 can be minus 2, minus 1, 0, plus 1, plus 2. That one's good. How about C? 6 minus 5. Minus 1 and half. Okay. You can't have a minus L, right? All the L are positive, right? Only the M sub L's can have negatives. Okay, so that was wrong. All are allowed. Okay. We found it. It's C. All right, 37. 40. This looks like a memorization. Who was the first chemist to recognize patterns in chemical properties of elements? The temptation here is to say Mendeleev, but he was not the first. The first one was, remember the one with the triads? Dobereiner. Dobereiner recognized the triads, the 3 elements that have similar properties. He grouped them in triads. You might be tempted to say Meyer also. Meyer was a contemporary of Mendeleev, and he put together his own periodic table, so to speak. But he didn't use it to do anything, whereas Mendeleev did. He actually predicted the existence of elements that hadn't been discovered yet. Not only that, he said, these are the properties they will have. These are the atomic weights they will have. Sure enough. Okay, so that was Dobereiner. 41. Mendeleev is given the most credit for the concept of periodic table of elements because what I just told you. I didn't realize I was stealing my own thunder. But he emphasized its usefulness in predicting the existence and properties of unknown elements. So B is the answer to that one. The complete electronic configuration of 10. All right, now we're going to have some fun. 10. So how do we know how many electrons we need? Try the periodic table, right? Where's 10? Right here. It has 50 protons. The neutral atom has 50 electrons. Okay, so we start our shorthand. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Oops. Nope. Yeah, 4s2, then 3d, 10, and then 4p6. Let me see how far I've got. There's 10. There's 10 more. That's 20, 30, 36. So I need what? 14 more. So 4p is 1, 2, 3, 4p. Then I go to 5s, 5s2, and 4d, 10. So that's 12. And I need, what did I say, 14? And I've used 12. I need 2 more. So we're down at that level of 5s, 5p, 2. There you go. So once you've written it out, you see what your choices are. Let's see. So we can look at the back of them. 5p2, 5p2. Okay, C and D is possible. A is possible. Then we look back of that one. Is 5d10? No, it's 4d10. There it is right there. Process of elimination. That one, let me see if I can do this. That one right there. Okay, and then you can check it. Be sure it's the same. Why? Because there's none of these up there. Since that none of these tells you that. There we go. None of these tells you that you got to look it all up. But we narrowed it down, and then you can check it with what you wrote and see if it's the same. And if it is, then you're home free. (44), 46, and 7. Only got 15 minutes. How many more do I have? I got a lot. Looks like I'll be coming back. The statement that the lowest energy configuration of an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals is known as, anybody?
Hund's rule.
Hund's rule, yeah. So if you have a p orbital, right, you got some suborbitals, and you've got 4 electrons, you got to do it like this, like this, like this first, before you can start pairing them up. That's what that means. 47. An element has the electron configuration krypton, and beyond that is 5s2, there's 2, 4d10, and 5p2. 4d10, 5p2. What are we talking about there? Krypton, right? Then you go down to 5. You got this one filled. Then you come across the transitions. That's all the transitions. And now you're up to here and here. Oh, that's 10. That's 10. So where is 10 located? Well, here's your line, right? It's on the metal side. Do we have a metalloid up there? No, so we call it a metal. All right. '48, '49. An element with electron configuration xenon, 6s2, 4f14, 6s2, 4f, 4f14, and 5d7. All right, so we're at xenon, and then we've gone through 6s, and then here we went down with that, finished that one off, and then we came back up here. So 5d7 would be 1, 2, 3, 4, 5, 6, 7. Is that right? Xenon is 54. Then we got 16, 23, 77. Yeah, iridium. So that's iridium. And it's a transition metal, transition element. We didn't have to do that. The fact that it has an incomplete d orbital, d level, means that it's a transition because all of these are d's. All right. Oh, 49. All the alkaline earths have the following number of valence electrons. Where are the alkaline earths? Who's in that family? Beryllium, magnesium, calcium. So how many valences do they have? 2, right? 2 valence electrons. That's why when they form ionic compounds, they always form 2+ charge. They give up those 2 electrons. All right, 50. Titanium has how many electrons in its d orbitals? Titanium. 50. Yeah, 50. Titanium. So we can just look at titanium. How many electrons in its d orbitals? That's 2. Scandium, titanium, that's 1, 2. 2 electrons. These questions are getting at whether or not you know how to use the periodic table. Another one, 52, iron. What about iron? So many electrons unpaired in its d orbitals. Okay. So how many electrons does it have in its d orbitals? Well, scandium, titanium, vanadium, chromium, manganese, iron. 6, right? 6 electrons in its d orbitals. How many suborbitals? We're talking about pairing now. Nice. D has 5, doesn't it? 5 times 2 is 10. It's 10 from one side to the other. So it has 1, 2, 3, 4, 5. So 6 electrons. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4 unpaired electrons. Yeah. All right. Okay, we need that diagram to answer the next one, 53. Which represents the ground state for nitrogen. So let's say nitrogen has 7. Yeah, 7. So it's 1s2, 2s2, 2p, 2, 4, 3. And they're also showing suborbitals. So 1, 2, 3 means like that, like that, like that. These guys are like this, like that. Okay? So we need 2, 2, and 3 independent. Okay, they're leaving this one off. Right? They're only going to the valence electrons. So let's see, it's either A, D, or E. And then the P's, A. Yeah, A is the right answer. But about 54. Let's see, and then we'll go back. Which represents the ground state for N minus? What does that mean? That means we added an electron. So it goes right there. Okay. So that would be B, right? No. E. E. Yeah, E. We good? Okay. 55. Yeah, 6 minutes. I'm gonna stop on time today because you need all the time you get for the lab. Because you got to do 6 titrations. First one will be the hardest one. After that, you'll be knocking them out. In which group do all the elements have the same number of valence electrons? Okay. So if they have the same number of valence electrons, they ought to be in the same family, right? So phosphorus, sulfur, chlorine. No, they're neighbors. Wrong direction, right? So A's false. Silver, cadmium, argon. Well, argon. None of those others are noble gases, are they? So it can't be B. How about sodium, calcium, barium? Well, sodium's an alkali metal. Calcium and barium are alkaline earths, so can't be them. Phosphorus, arsenic, selenium. Phosphorus, arsenic. Oh, we were doing good until we got to this one. All right, so none of them. All right, still got some time. 58, 59. One of the following elements which has occupied d orbitals of the following elements, which has occupied d orbitals in its ground state, neutral atom. Occupied d orbitals. That's a tricky question because the first thing you think of is say, all right, I'm going to go to the transition metals and see if they're there. If you go to the transition metals, that just means that those are the orbitals being filled. But some of these elements have already gone through the d orbitals once and got them filled, and they're moving on. So based on the question, there may be more than one that has d orbitals filled. What we have to do is look at them one by one. Let's see, barium. Barium's way down here. So it's already gone through this one and this one. It's got filled d orbitals. So we found our answer. If we go through the rest of them, you'll find that calcium, nope. Silicon, phosphorus, nope. And chlorine, nope. No d orbitals for those guys. Just barium. Of the following elements, which needs 3 electrons to complete its valence shell? To complete its valence shell. That's another tricky question. Well, barium would either have to go all the way across here or back up 2. So that it can't be barium. Calcium would have to back up 2. Silicon needs 1, 2, 3. It's not complete. It's got to go all the way over to noble gas. How about phosphorus? Phosphorus. 1, 2, 3. Yep, that's it. It will complete its valence shell with 3 electrons. Chlorine only needs 1, just to make the picture complete. All right. I'm gonna go right up to the wire. 62. Which of the following atoms has 3 electrons in p orbitals in its valence shell? 3 electrons in its valence in p orbitals. So that means we're over here. 3 electrons. 1, 2, 3. It's got to be one of these. Nitrogen, phosphorus, arsenic, or antimony. Oh, bismuth? Oh, I didn't go down far enough. Bismuth. Yeah, bismuth has 3 electrons in its p valence shell. Uh, 66. Which of the following is the highest energy orbital for a silicon atom? The highest energy orbital for silicon. Well, we filled n equals 1, n equals 2. Now we're at n equals 3, and we're at 3p2. Right? 3p2. So D is the answer. There you go. Got 40 seconds. Can I do the other one? Yeah, we can do 67. Okay, which of the following process represents ionization energy of bromine? Ionization energy. We need the element. It has to be a gas. And it has to eject an electron. And what is it left behind? Like that. Right. So there's C is the answer. Okay. All right. So I need to come back and start with 68. 68. Order the elements sulfur, chlorine, fluoride in terms of increasing ionization energy. Okay. Increasing ionization energy. Actually, this is first ionization energy. That's understood. Sulfur, chlorine, fluorine. Sulfur, chlorine, fluorine. Okay. So where are they located in the periodic table? Hold on a second. Start over again. Number 68. Order the elements sulfur, chlorine, and fluorine in terms of increasing ionization energy. Increasing ionization energy is understood to be the first ionization energy. If they don't say second or third, then they mean the first ionization energy. So where are these located in the periodic table? We look at the periodic table and find that sulfur is down here. Chlorine is right next door. And fluorine is like that. Right? So the halogens are here, like the chalcogens are here, so oxygen would be there. So what's the trend? Lower left to upper right, increasing ionization energy. So it should be sulfur is less than chlorine, which is less than fluorine. So it should be sulfur, chlorine, fluorine, A. All right. '69. Order those same elements in terms of increasing atomic radius. Increasing radius. I should say atomic radius. We didn't talk about ionic radius, but I should be specific. This is atomic radius. So these are neutral atoms. How big are they? Right. So for the same sulfur, chlorine, fluorine, sulfur, chlorine, fluorine. All right, what's the trend? As we go from left to right, the radius decreases. And as we go from bottom to top, the radius decreases. So the trend is increasing is upper right to lower left. Right? This is increasing. Okay, so if we're going to put them in order of increasing, then fluorine would be the smallest one. And then the next largest one would be chlorine, and the next largest one would be sulfur. So it's the other way around from the previous number 68. This one's fluorine, chlorine, sulfur, which would be D. D is the answer to this one. All right, 70. Let's see, can I get those three on there? Yeah, there we go. 73. 73 says, of the following elements, which has the lowest first ionization energy? Okay, the lowest first ionization energy. Remember, ionization energy increases from lower left to upper right. So we want to find the one that's the furthest down and the furthest to the left. Right? Where's barium? Barium is in the lower left-hand corner. Calcium is above barium. Silicon's to the right, phosphorus to the right, chlorine's to the right. Barium has to be the lowest ionization energy. There. Okay. '74. Of the following elements, which is most likely to form a negative ion with charge of a 1- charge? So the same elements, but now we're looking for which one is most likely to form a -1 charge. Okay. Let's write these out. Barium, calcium, silicon, phosphorus, and chlorine. All right. Remember, elements form charges because they want to be like a noble gas. So how do they get to be a noble gas? If they're on the far left-hand side of the periodic table, it's simpler to lose an electron and go backwards to the nearest noble gas. So those become positives. Barium is on the left-hand side. It loses 2 electrons, so it gives it 2 positives. Calcium's the same way. Loses 2. How about silicon? Well, silicon's funny. Silicon could either be a plus or a -4 depending on its environment. Right? It can go either add 4 or lose 4. Phosphorus is a pnictogen. So we need to go from phosphorus to sulfur to chlorine to argon. It needs to gain 3 electrons. So phosphorus would be a 3-. Chlorine is a halogen. It's 1 step away from the noble gases. So this one needs to gain 1 electron to give it that negative charge. And all the halogens are this way. So the answer here is E. Yes, E. That's your answer. '75. Which of the following atoms has the largest ionization energy? Okay, so we got oxygen, lithium, neon, beryllium, and potassium. Okay, think about this. A certain amount of energy is required to remove an electron from a neutral atom. Right? And if the electron is a valence electron, it takes a certain amount of energy. But if the electron is a core electron, it takes about 10 times as much energy, I think, rule of thumb. So which one of these is going to lose an electron from the core, right? Oxygen has 2 electrons. It can lose, right? In its valence. Actually, it has more than that. Oxygen has 6 electrons. It can lose valence electrons. It has 6 electrons. Lithium has 1. Neon has none. Beryllium has 2. Potassium has 1. Those are the valence electrons. So neon, when it loses an electron, it comes from the core. It has no valence electrons, right? These are all core electrons. Now, technically speaking, neon's, let's see, neon has, 2s2 and 2p6. So these are technically the valence electrons, so it has 8. But those orbitals are completely full. They're happy the way they are. If you try to take electrons from these, it's the same as taking electrons from a core. So the neon is going to have the highest first ionization energy. All right, that was 75. Let's scroll it a little bit. 77. Have we visited this topic before? Which of these arrangements of electromagnetic radiation are in order of decreasing frequency? Decreasing frequency. Okay. Decreasing frequency, this is the way I look at it. Decreasing frequency means increasing wavelength. That's easier for me to understand. Increasing wavelength would be decreasing frequency. So which one has the, let's see, visible ultraviolet X-ray. Let's just do it. Visible UV X-ray. Is that increasing wavelength? No, that's a very short wavelength. This is shorter than visible, so it's the other way around. Right? So that's not it. How about B? Radio visible ultraviolet. Radio visible UV. Increasing wavelength? No, it's the other way around. Increasing this direction. Right? Okay, so that one's not it. How about C? Ultraviolet visible infrared. Ultraviolet visible infrared. Increasing wavelength. Ultraviolet visible, that's the one right there. That's how I look at it. It's easier for me to wrap my mind around wavelength than it is frequency. Mm-hmm. 77, 78, and we'll do, I don't know if I can do it fine enough. Let's do them one at a time. 78. Increasing wavelength. All right. 78. 78 is the same as the 77. But it's made the transition for us already. Decreasing frequency is the same as increasing wavelength, so it's the same answer. Ultraviolet, visible, infrared. 79. Which of these types of electromagnetic radiation are arranged in order of decreasing energy? Okay, decreasing energy. When we look at that, we need this expression, Planck's constant, and that's the one that has wavelength in it. Okay, so decreasing energy, these are inversely proportional. As this goes up, this goes down, or as this goes down, divisor goes down, this goes up. So if we want decreasing energy, we need increasing wavelength. So increasing wavelength would be the same as 77 and 78. Decreasing energy is increasing wavelength. Ultraviolet, visible, infrared. $80, yeah, we're going to do 80. There we go. In the quantum theory, the magnetic orbital momentum quantum number is most directly associated with which property? All right. So we got N, L, M sub L, and M sub S. What are these associated with? Let's see. Magnetic orbital momentum. Okay, this one is energy. And it's associated with distance from the nucleus. Okay, this one is the angular momentum, I think. Angular momentum. Yeah, this is angular momentum. And this is associated with shape. Okay, this is magnetic. And this is associated with orientation. And this is electron spin. Okay, so the magnetic is associated with orientation in space. The best way I think of it is for the p orbitals. Right? P orbitals are a value of 1, right? That's equal to 1. M sub L equals 1, which means, oh, excuse me, L equals 1. Sorry. If L equals 1, then M sub L can either be -1, 0, or +1. And I look at those orientation in space, 3 dimensions. There's X, there's Y, and there's Z. So they can be, their shape is dumbbell. So it can be like this on the x-axis, this on the y-axis, or this on the z-axis. It can be this way, or this way. Okay, so the answer to that would be let's see, 81? 81? Yeah, 81. Okay. I can do better than that. 81, there we go. In the quantum theory, the angular orbital momentum quantum number is most directly associated with which property? That's the one above. This is associated with shape. The angular momentum, L, is angular momentum. And that's shape. Right? So the S is spherical. P is dumbbell. And SPD. D is also sort of a dumbbell, but it also has a donut. One of its orbitals is donut shaped. And then F is just wild. All right, so the answer to that one's D. Okay. Let's see. I do 84. 84. Select the correct electron configuration for copper. Okay, they're allowing us to use the abbreviated form. So how many electrons in neutral copper? We have 29. If we take copper and work our way backwards through the period until we get to alkali metals and then jump up one period and go to the other end, we'll find the noble gas. So if we do that, we go back to argon. And argon has 18. So we've got the basic structure, the core structure is argon, and then past argon is potassium. Now we're down to 4s. And then we come across to 3D. So how many do we go to get to copper from 3D? Well, we just count across, right? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. That's 9. There you go. So that should be, oh, okay. Here's one of the anomalies. We didn't talk about these in detail in the lecture part. This is what you would expect. But remember, the Aufbau principle says electrons are inserted into orbitals in order of energy, increasing energy. This puts electrons in positions where they're less stable. They're higher energy. The idea is once you've gotten to this point, see 1, 2, 3, 4, 5 suborbitals of D. We would do 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, this is so close to a complete d orbital. The lower energy state is to take one of these electrons from here and put it over here. So the electron configuration of copper actually is 4s1 3d10. Okay. There's another place that this happens. Let's see. 1, 2, 3, 4. Chromium, 24. So chromium would be like this. And we would think that chromium would be 4s2, 3d4. Right? 1, 2, 3, 4. Yeah. That's what we would expect. But similar to this one, 1, 2, 3, 4, 5, 1, 2, 3, 4 for that D. It's a more stable energy state to take one of these and put it over here. And a half-filled orbital with the sublevels like this is more stable. Okay. And that was 84. 85. A5. Which of the following equations correctly represent the process involved in electron affinity of X? X. What does electron affinity mean? How willingly does the X accept an electron? In other words, it gives up energy, right? It's a negative energy. So the higher the negative energy, the more affinity X has for an electron. But we need a gas, right? Remember why we need a gas? Because we don't want phase change energies to interfere with our calculation for our determination. If you have to change phases here, say this starts out as a metal. You've got to go through a liquid and a gas, put a lot of energy into it before you get to the place where you're going to actually accept an electron. And that value would be meaningless. So it's going to accept an electron as a gas and produce a negative ion as a gas. Right? And that's C. That's electron affinity. '86. We ought to be getting close. 86 and 87. All right. Which of the following lists of atoms are arranged in order of decreasing atomic radius? All right. Decreasing radius. Decreasing atomic radius. So the radius decreases from lower left to upper right. Right? Decreases like that. So what we need is, let's see how many of these are similar. Lithium, oxygen, nitrogen, fluorine. Lithium, oxygen, nitrogen, fluorine. Okay, B, that's A. B has the same ones. C has the same ones. D and E are different. So D is sodium, strontium, oxygen, and fluorine. And the last one is calcium, cesium, sulfur, and selenium. So what we need to do is look at the, since we don't have any oddballs in here, we can start from the top and work our way down till we find the answer. Lithium, oxygen, nitrogen, fluorine. So where's lithium? Lithium is way over on the left. Okay. Oxygen is over here. Fluorine is right next door. And nitrogen. And nitrogen is right here. Okay. All right. So lithium, oxygen, nitrogen, fluorine, these are backwards, right? From left to right, you should decrease atomic radius. So if we put oxygen in front, excuse me. No, this would be the right. This would be the right order. But A is wrong. A has oxygen and nitrogen reversed. Lithium, nitrogen, B. B has them in the correct order. Right? So they're decreasing this way, this way. All right. Okay. We didn't even have to look at those others. 87. Consider an atom traveling at 1% of the speed of light. We got an atom. Its velocity equals 1% of c, speed of light. The de Broglie wavelength is found to be, okay, the de Broglie wavelength of this atom is 1.46 times 10 to the minus 3 picometers. Which element is this? All right. So let's work this one from the back end. How do you identify an element? There are only two ways. Either you know the atomic number, right? We're not going to get the atomic number for that, I don't think. So we've got to look at the molar mass of the element. So we need mass per mole. Okay. All right. Now we didn't talk about de Broglie. De Broglie was I think the common term is a polymath. He was a master of several subjects. And he proposed that everything in the universe can be represented as a wave. Even I can be represented as a wave. So mass and waves are interchangeable. So we're given this information, and now we need to determine molar mass. Okay. So how are we going to get at mass? Well, Einstein said that mass is equal to, energy. My mistake. Energy is equal to mass times the speed of light squared. Okay, and my mind's gone blank. Well, the energy of a wave is equal to Planck. Max Planck said this, but that doesn't help us any. We have wavelength. So we have this one, that one divided by wavelength. There we go. Right, so at the speed of light, this one is equal to that one. Right? MC squared is equal to Planck's constant times C divided by wavelength. And the mass of this atom then would be equal to, this becomes a divisor, H, C, there, and C squared, like that. That cancels this one, cancels one of those. Okay? But for de Broglie's application, we don't want C, we want the actual velocity. Right? So we're going to say, for our purposes, mass is equal to Planck's constant. Actually, let me write this one. Planck's constant's in the numerator, divided by the de Broglie wavelength times the actual velocity. So what is the actual velocity? 1% of the speed of light. So if the speed of light, if C equals 2.9979 times 10 to the minus 8 meters per second, then the velocity of the atom is 1% of that. Right? So it's traveling slower. Right? You need a 1% change. The best way to do that is, what is the fractional equivalent of 1%? 1% is equal to 0.01. Right? 10% would be 0.1. 100% would be 1. So the multiplier here is 0.01 times 0.01. So that's 10 to the minus 2. That means 2.9979 times 10 to the minus 10 meters per second. That's our velocity. Okay. All right. So what is this mass going to be in? What units of measure? This is in, let's see, Planck's constant is in joule seconds. Okay. This is in meters, and this is in meters per second. Okay. So let's find out what is the mass. Let's use this to find the mass of that atom. Okay. So mass of the atom is Planck's constant, which is 6.626 times 10 to the minus 34 joules seconds. And that's divided by the wavelength. The de Broglie wavelength is picometers. That has to be in meters. What's a pico? A pico is 10 to the minus 12. Right? So 10 to the minus 12 times 10 to the minus 3 is 10 to the minus 15. Right? So that's 1.46 times 10 to the minus 15 meters is the de Broglie wavelength. Right? So that goes right here. 1.46 times 10 to the minus 15 meters. And then oh, that was so dumb. Speed of light is 10 to the 8th meters per second. So this is 10 to the minus 2. That makes this 10 to the 6th. There we go. Oh, so the speed of light, 2.9979 times 10 to the 6th meters per second. Actually, the 1% of the speed of light. Okay, now we can calculate the mass. But what are the units going to be? Well, this is one of those cases where the meters cancel fine. And the seconds become seconds squared. So joule seconds squared. And so what would that be? That would be 1.5139 times 10 to the minus 25 joules seconds squared. All right, what is a joule? This is a case where we can't cancel units unless we know what a joule is. Remember when I described earlier, what is a joule? How do we get the energy unit? Okay, we go back to this expression. Kinetic energy equals 1/2 mv squared. So in this case, this is a joule, this is a kilogram, and velocity is meters per second, but that's squared. So kilogram meter squared per second squared is what this is equal to right here. Kilogram meter squared per second squared times second squared. So second squareds cancel. And let's see. Oh, no, I'm sorry. Here. These do not cancel. This is per meter squared. So now the meter squared cancels because this is in the numerator here, this is in the numerator here of the denominator. So this puts it in the denominator, meter squared in the denominator. Seconds goes up here for second squared up there. Now second squared cancel meter squared. So this gives us kilograms. 1.5139 times 10 to the minus 25 kilograms. That's per atom. Okay? Now that we've got that, we want mass per mole. So we've got a dimensional analysis problem. 1.5139 times 10 to the minus 25 kilograms per atom. But we want grams per mole. So let's change them one at a time. Kilograms on the bottom to cancel that one. Grams on the top. 10 to the third grams per kilogram. Okay, so that's grams. Now we need to change atoms to moles. So how many atoms in a mole? We need moles on the bottom, right? Grams per mole. So how many atoms in a mole? 6.022 times 10 to the 23rd atoms per mole. There we go. So now we've done all the atoms. There we go. Now we got grams per mole. Now we can determine the molar mass of this atom or this element. Right? And that should come out to something like 91.2 grams per mole. Now all we have to do is go to the periodic table and find the one that's closest to that, 91.2. And it looks like we're at zirconium. Okay? That's a lot of work. And that's a prime extra credit question. How about 88? Let me erase some of this stuff so we can talk about 88. All right, 88. In an investigation of the electronic absorption spectrum of a particular element, it's found that a photon having wavelength 500 nanometers provides just enough energy to promote an electron from second quantum level to third. So this promotes an electron from n equals 2 to n equals 3. From this information, we can deduce what? The energy level of 2, the energy level of 3? No. This tells us the difference. Right? This tells us the energy jump, the energy that came in here and caused the electron to go from this level to a higher level. It absorbed that energy. That tells us the difference between these two energies. Energy of 2, actually energy of 3 is higher than 2. Right? So energy of 3 minus energy of 2, it tells us the change in energy. The difference in energies between N2 and N3. That's D. That's what it tells us. All right. Let's see. We need that table up there. So let's see. Let's do it like this. 89. 89. In the hydrogen spectrum, what is the wavelength of light associated with, using that table? What is the wavelength of light associated with the 3 to N1 electron transition. So if it goes from N3 down to N1, then it's going to give off energy, right? That's equal to E, right? Planck's constant times frequency. But the question is, what's the wavelength? So we need the expression Planck's constant times C divided by wavelength. Okay. So using these differences, if we go from 3 to 1, then final minus initial is the energy jump. So the final is 1. And 1 is minus 2.178, minus 2.178 times 10 to the negative 18. This is a change in energy. This is final, right? Final minus initial. And initial is going to be 3. So 3 is minus 0.242 minus 0.2420 times 10 to the minus 18. And this is in joules. Joules. Okay, so what's the difference here? Well, this one times that one is a positive. Is that right? Yeah, that's right. This one becomes positive, that's negative. Well, actually what we need is the absolute value. How much energy was given off? Right. So the absolute value of that expression is 1.936 times 10 to the minus 18 joules. Okay, and this is equal to Planck's constant, 6.626 times 10 to the minus 34, I believe, joule seconds. Right. Times the speed of light, 2.9979 times 10 to the minus 10 to the 8th. I almost did it again. Meters per second. Divided by the wavelength. That's our unknown. Right. So we solve for the wavelength. Wavelength comes over here. Energy goes down here. We divide energy into that one, and energy into that one times this one. So the change in energy is equal to, actually the wavelengths, I'm sorry, the wavelength is 1.026 times 10 to the minus 7 meters. Now, is that one of our answers? Yeah, E. Rounded off, 1.03. Okay, that was 89. Do we want 90 also? What's the wavelength of light that is emitted when an excited electron in the hydrogen falls from 5 to 1? Okay. So we're going to go from 5 to 1 this time. 90. We're going from N5 down to N1. So in this case, we're also going to emit light, and we want to know the wavelength. Okay, so it's basically the same thing. We set up, just like we did before, the wavelength equals H times C, energy. Energy equals, the change in energy equals this expression. So wavelength is equal to Planck's constant times speed of light divided by the change in energy. Okay, So what's the change in energy? Well, 5 is lower and lower energy as you go higher. So 5 is negative 0.08712 times 10 to the minus 18 joules. And N1 is the same as it was before, minus 2.178 times 10 to the minus 18. So the difference between those two, the difference in energy here is, let me calculate it. Oh, I missed my calculator. All right, so we're going to put it in this way. Planck's constant, joules seconds, times the speed of light, and divided by the absolute value of minus 2.178 minus a minus, which will be a plus 0.0812. Oh, wait, 712, excuse me. 712 times 10 to the minus 18. So this one right here, since they both are times 10 to the minus 18, I just factored that out. But we want the absolute value. And if we calculate that correctly, we get a wavelength of 9.50 times 10 to the minus 8 meters. All right, that's 90. Ooh. Pardon me for a moment. All right. Next. 91. Which of the following is a reasonable criticism of Bohr model of the atom? '91. Reasonable criticism of the Bohr model. Remember, the Bohr model was a planetary model, right? Had the electrons in circular orbits and the nucleus here. Okay. It makes no attempt to explain why the negative electron does not eventually fall into the positive nucleus. Well, yeah, that's possible. It does not adequately predict the line spectrum of hydrogen. No, it does that very well. C, it does not adequately predict the ionization energy of the valence electron for elements other than hydrogen. Well, that's true. I mean, it doesn't do that. That's a reasonable criticism. It does not adequately predict the ionization energy of the first energy level electrons for one electron species for elements other than hydrogen. It shows, and that's D. E, it shows the electrons to exist outside the nucleus. Now, that's reasonable. You know what? A is a reasonable criticism. And C is a reasonable criticism. All right, so which is the most reasonable? Well, the most reasonable would be C. It does not adequately predict the ionization energy of the valence electrons for elements other than hydrogen. But A is a pretty good one. All right. So actually, any one of these would be a reasonable criticism. This is the best one. This is the second, and this is the third. So that's not a well-written question, I must say. Okay, 93. Which of the following statements is or are true? So we got to look at each one of them. How about Roman numeral 1? An excited atom can return to its ground state by absorbing electromagnetic radiation. What happens when an excited atom returns to its ground state? An electron returns, so it goes from high energy to low energy. Right? So if it goes from high to low, it has to give up energy. Right? So 1 is false. How about 2? The energy of an atom is increased when electromagnetic radiation is emitted from it. That's false for the same reason. When energy is emitted, the energy level of the atom decreases. Number 3, the energy of electromagnetic radiation increases as its frequency increases. Yes. Increase frequency, increase energy. That one's true. How about number 4? An electron in the N4 state in the hydrogen atom can go to the N2 state by emitting electromagnetic radiation at an appropriate frequency. Yes, If it drops from a high level to a low level, it gives up energy. That one is also true. And 5. The frequency and wavelength of electromagnetic radiation are inversely proportional to each other. That is true. They're inversely proportional because you multiply them together, frequency times wavelength, and you get the speed of light. Right? This is an inverse proportion. That's a constant. Products of variables equal to a constant are inversely proportional to one another. So this one is also true. So 3, 4, and 5 are true. That would be D. All right, 93, 94. Let's see, yeah, 94. 94. Consider the following representation of a 2p orbital. A 2p orbital. Okay. Which of the following statements best describes the movement of electrons in a p orbital? Okay, A. The electrons move along the outer surface of the p orbital similar to a figure 8. No. That's false. We cannot predict the movement of electrons if we know their energies. And the 2p represents energy. That tells us what the energy level is. So if we know the energy, we can't predict where they are. The shape of this orbital is simply a probability. Of finding the electron. In that volume of space. Okay, that's all that means. So which one matches that? Well, if we look at each one and work our way down, we find that the best answer is that the electron movement cannot be exactly determined, right? You cannot tell based on the Heisenberg's uncertainty principle, right? I'm curious. Let me check something for a second. In useful information. Did I put Heisenberg in here? Maybe not. No, I guess not. Okay. That was 94. Okay. 95. 95. Here we go. Okay, so E is the best answer for 94. I need to give this one a rest. Let's try blue. So we got 95. How many electrons can be contained in all of the orbitals with n equals 4? All right, we start at n equals 4. That means how many L's can we have? Well, we can have 0, 1, 2, and 3. How about m sub L's? Well, this one we can only have 0. This one we have -1, 0, and +1. This one is -2, -1, 0, +1, and +2. And 3 would be -3, -2, -1, 0, +1, +2, and +3. And then m sub s is just 2 times each one of those. Right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 32 electrons. Okay? That's not dark enough. I need something darker. $95. 96. You can get 97 also. 96. Okay. The small but important energy difference between 3s, 3p, and 3d orbitals are due mainly to 3s, 3p, and 3d, right? Because remember, the principal quantum number is reference to energy. So the energy of these should be very close to each other, but they're not the same. They're not exactly the same. So why are they different? Well, they're different because of the shapes of these orbitals. And that goes back to a discussion of the penetration effect. The 3s penetrates closer to the nucleus than the p does. And the p penetrates closer to the nucleus than the d does. Okay, so that explains the difference in their energies. How about 97? Which of the following was not an elemental property usually predicted by Mendeleev for unknown elements? Okay. A, electron configuration. All right. When Mendeleev was active, there was no understanding whatsoever of the internal structure of atoms. Subatomic particles had not been described. Now, he knew the atomic mass, he knew the density, he knew the boiling points, he even knew the oxide formulas of all the metals and many of the nonmetals. But he knew nothing of electron configuration. Which makes his accomplishments even that much more unbelievable. 98. Which of the following atoms or ions has 3 unpaired electrons? Okay, A, B, C, D, and E. We need 3 unpaired electrons. Okay, nitrogen. So what does nitrogen look like? Well, it's got 7. So we have 1s2, 2s2, and 2p3. 1, 2, 3, there. Okay, that's it. We found our answer. Right, we could draw out all the rest of them, but multiple choice says that's our answer. (101). Okay, an element E has the electron configuration krypton. Let's see, that's 36, 5s2, 4d10, and 5p2. The formula for the fluoride of E. So this is equal to the element E. All right, if you're going to form a fluoride from E, what's the charge on fluorine? It's going to be a -1. It's a halogen, right? -1. So what's the charge on this one? Well, Most likely, you have two choices. We want to get from here back to here by losing valence electrons. These are your valence electrons right here. 2 and 2. It could lose these two, the P's, because they're higher energy than the S's, which would make it, right, 2 plus, which means we need a 2 here. So EF2, do we have an EF2 up there? No. So we go to the next one. We lose 2 more. If we lose 2 more electrons, that means a 4 plus. That means we need 4 of these. So EF4 would be the next possibility. And there it is, B. (104). (104). Which of the following atoms would have the largest second ionization energy? Okay, so what do we have? Magnesium, chlorine, sulfur. Magnesium, chlorine, sulfur, calcium, and sodium. All right, so second ionization energy. What we're looking at here is possibly the second ionization energy gets hold of an electron that's in the core. Do we have any there that only have one electron in the valence shell? Let's see, magnesium has 2 electrons in the valence shell. Why? Because it's an alkaline earth. It's in the second column. Chlorine has 7. Sulfur has 6. These are valence electrons. Calcium has 2. Sodium has 1. If you take that electron out and then try to get the second one, you're in the core. That makes sodium the best candidate for the largest second ionization energy. Okay, 107. Let's see. Which of the following concerning second ionization energies is true? All right. A, all of aluminum, is higher than that of, the second ionization energy of aluminum is higher than that of magnesium. Well, first of all, is that true? Second ionization of aluminum. How many valence electrons does it have? Well, aluminum has 3. 3 of them. Okay. How about magnesium? Magnesium has 2. So the second ionization energy of magnesium aluminum is higher than that of magnesium because magnesium wants to lose the second electron. Well, actually, let's use the trend. Ionization energy increases from left to right. So aluminum should be a higher ionization energy the first place and the second place. So aluminum has a higher ionization energy than magnesium, not because magnesium wants to lose the second electron, but because aluminum wants to hold on to its electron more. How about B? Aluminum is higher than that of magnesium because the electrons are taken from the same energy level, but the aluminum atom has 1 more proton. There's the key. The larger effective nuclear charge of aluminum is why the second ionization energy is higher. 108. Consider a planet where the temperature is so high that the ground state of an electron in the hydrogen atom is N equals 4. Let's see, 108. Okay, so the ground state of hydrogen is that the electrons in the fourth is N equals 4. Okay. What's the ratio of ionization energy for the hydrogen in this planet compared to that on Earth? So on Earth, hydrogen, 2, 3, 4, hydrogen has ground state here at 1. So how much energy does it take to go from here to infinity? And how much energy does it take to go from here to infinity? That's the ionization energy that they're talking about. What's the ratio of the two? Well, what we need is values that we don't have right there. We have to go back to that chart for, it goes all the way back to 92. Oh, that's not it. No. Where is it? Must be further. It's in the 80s. Here we go. Right. Okay, so if we're going from this level to that level, what's the energy level of infinity? It's 0. It's 0 for both of them. Right? So the ionization energy is going to be, how much energy do you have to put in? So it's going to be a positive amount. We're going to go from here to there. So what's the energy level for this one? We're going from 0 to there, so it's going to be a positive amount of energy that has to be added from here to the fourth level. The fourth level is minus 0.1361. Times 10 to the minus 18 joules, is it? Yeah. But here, this energy level is 2.178 minus 2.178 times 10 to the minus 18 joules. Okay, that's how much energy that we have to put in to promote the electron to 0 energy. Okay, so let me see. So the ratio, the question was, I got to go back to the question now. 108. There we go. What's the ratio of ionization energy for hydrogen on this planet compared to that on Earth? The ratio, this one compared to that one. So the ratio of this energy to that energy would be what? It would be 0.136 times 10 to the minus 18 divided by 2.178 times 10 to the minus 18. So these divide, cancel each other. We need to divide 0.136 divided by 2.178. 0.136 here, 0.178. Okay, well, that gives me a value, but it doesn't fit with what they're discussing here. C 1/4, 1/16, 4/16. So let's see what those fractions are. I know 1 to 4 is 0.25. What's 1 to 16? So 1 enter 16 divide. 16, 1/16. This value is actually equal to 6.24 times 10 to the minus 2. And 1/16 is equal to 6.25 times 10 to the minus 2. So that's it. It's 1 to 16. Okay. Now, the other way to work this problem is to use the formula in useful information. Here, energy equals minus 2.178 times 10 to the minus 18 times z squared over n squared. And you can calculate this one for that one and this one for this one and ratio them. And you'll get the same answer. I just did it a little bit different way than is reported in the worked problems that I gave you. And a new marker. All right. Are we close to the end? That's it. We are done.